Okay, so let me share my screen first. Everybody, can you see my screen?
Yes. Yes, sir.
Okay. Okay. As you can see the title, today we'll be discussing about high voltage direct current, that is HVDC system. So it is very important, that system. The first of all, let's go to the next slide to understand that what is that HVDC and where is it used. So everybody see this picture. So leftmost side, you can see there is a wind turbine system that is placed inside the ocean. This means this is an example of offshore wind farm, and that offshore wind farm is connected to the onshore, that is mainland grid system. But in between, you see, right after that wind generator, there is AC substation. So in the AC substation, there are transformers that increases the voltage that is produced with the help of wind generator. And then after that, you can see there is offshore DC converter. This means that AC is converted into DC. And as you can see, this green colored line, that is basically the DC or the high voltage DC line. The distance is kind of about 80 kilometers. Now, the question is why it is converted into DC? Because here you see on shore, I mean, after coming on land, again that DC is converted back into AC. So the question is, what is the motivation or why this portion is DC? So as you can see, because this portion, that 80 kilometer, that is still, inside sea. I mean, this portion is still, there are water here. And people cannot use power in this portion. So if it would be AC, then there would be much more losses, like I square R loss and I square X loss. This means reactive power loss. That's why, because people cannot use the power in this like 80-kilometer distance, or even it could be much more. So that's why it is converted into DC, because if it is DC, then there is only I square R loss. There is no I square X loss. That is the motivation to use the DC. So, and it is the like high voltage, so that here you get the high power voltage multiplied by the current to match with the required grid voltage. That's why this portion is that high voltage DC, HVDC. So everybody understand the context of HVDC or the DC?
Dr. Ali, I have a question.
Yeah.
So the connection between the office sphere and the power electronics, is it underground or above the sand of the sea?
Underground.
So like it's buried, right?
Yeah. Underground. So,
but why do we bury it, Dr. Ali? Why do we don't have it like on the surface of the sand of the sea?
Oh, because there is like, wave, there is current. So that is very challenging.
Okay. Because of the waves of the sea, right?
Yes, exactly.
Okay.
Because, it is very challenging. Even in this buried configuration is also challenging. It's very difficult because always there is, wave and the current. So that's very difficult. So now go to that next slide to understand much more. Again, the benefit of having the DC in this portion.
Dr. Ali, I have one more question, please.
Oh, sure.
Why do we have power like tower for IC substation and another tower for the DC converter? Why we don't have the same power that to reduce the cost of towers?
Okay, so you know that first of all, on the left side, which is the wind turbine, that produces a small voltage,
Yes.
kind of 690 volt. That is the typical from on wind turbine.
Mhm.
That's why immediately you need a step up transformer. That's
Yeah.
why there is transformer here. Because we want to make here the high voltage DC. In order to get enough DC, high amount DC, you need high voltage here. That's why first there are transformer here, and it is called the substation because not only there are transformer here, but also there are some controllers, and then to monitor the blade situations, so generator conditions and other. That's why it is called the substation. And then that high voltage is converted into DC with the help of big size of DC converter. That's why this is a DC converter station. Is this fine?
My question, Dr. Ali, why we have like two towers for power electronics? Why we don't have one instead of two? Would it be
Oh.
better for us, like instead of having two power towers? I mean,
Oh, you mean that the number of tower here?
yes.
Oh, that
Like
is.
if you see, Dr. Ali, you have like one tower for IC substation and another tower for DC converter. Why we don't have the same tower for both of them?
Oh, so it could be, but you know, so because of some benefit, like first it is converted. So your question is why it is not placed all in together, right?
Yes, yes.
Yeah. So because there is some benefit in having in that way to separate out the operation or the functionality. So it is like just converted into AC and then let go some AC cable. And because you know, so this DC converter, I mean, later I will show you a picture. This is a huge thing. I mean, that all HVDC control, I mean, there is controller on this side and there is controller on that side. And it's a huge technology, that HVDC. That's why it is separated out.
Because of the size, right?
Yes, yes.
Okay.
And some economical and then technical benefit.
Okay.
So therefore, today our main concentration will be like this portion, so HVDC portion. And also we will be looking the how power is produced, what are the technologies available to capture wave energy or the ocean energy. Okay, so moving forward, now as I said that our concentration is that HVDC portion or the DC portion. So everybody see this slide, like I have mentioned, you see the left side, this is the AC tower. And on the AC tower, you know, this is one three-phase system. And then this is other three-phase system. So, and then on the right side, this is the DC tower. In the DC tower, you can see only two cables, one for positive and then other for the negative terminal. Now, as you can see, because this is three-phase system, so you need A phase, B phase, C phase, three-phase coil, three-phase coil. So I have written, you know, first bullet point, you need less cable. Because here you need only two cables. On the other hand, here you need, even though you consider on single circuit, you need three cables. So another three cables here. It is called the like double circuit transmission line. So consequently, less loss. As I already told, if you put the AC on that zone in 80-kilometer area, then there are not only I square R loss, there is I square X loss. So here you see there is only I square R loss. So the amount of loss is also less. Now say I have written there is no skin effect or capacitive effect. So this is very important. So probably you all know the skin effect. Skin effect is if you compare a AC cable versus a DC cable. On AC cable, current the high current flows on the surface or on the skin of the cable, and less current flows inside the cable. The reason is that the inductance is higher inside the AC cable. On the other hand, in case of the DC, current flow or the distribution of current flow is uniform throughout the cross section of the cable. This means in case of the DC, amount of current flow is equal on the surface and inside, anywhere. That's why it is called uniform. On the other hand, in case of AC, as I told, much current flow or the higher current flow on the surface than the inner side. Because higher current flow on the surface or skin, accordingly it is called the skin effect. So in case of the DC, as you can understand, because of the uniform current distribution, there is no skin effect. Now, no capacitive effect, this means that if it would be AC, then always there are some kind of the leakage, capacitor leakage loss. But in this case, if you calculate the capacitive reactance like XC equal to 1 over 2 pi FC, everybody know. But in case of the DC, frequency is 0. Therefore, XC becomes infinity. So because if XC becomes infinity, this means no current flows. So this means there is no capacitive effect or no capacitive loss. That is the meaning. So therefore, these all are the like less cable, less loss, no skin effect, or no capacitive effect are the main points. Now, what is the type of the HVDC cable that is used? I have written, you see, due to its mechanical strength, flexibility, and low weight, XLPA, it is a special type of cable. It is called cross-linked polyethylene type of cable is used for HVDC transmission system. Even, currently lots of research is going on what could be the cable type in that portion. So everybody is fine so far. What is the motivation to go with the HVDC transmission system for the offshore wind farm? Okay, so moving forward, as I said, today we'll be also looking ocean energy systems. So for the ocean energy systems, you see here some highlights about the ocean energy systems. I said, according to a report, this is mainly the Department of Energy report, wave energy provides 15 to 20 times more available energy per square meter than either wind or the solar. And this energy resource is part of the huge amount of untapped energy available in the ocean, which are typically in the form of ocean currents, ocean wave, tides, etc. This means we have to utilize the ocean current, ocean wave, and tide by some technology. And ocean current and ocean wave are the most commercially viable resources that have been studied or analyzed so far, and both have undergone limited commercial development. However, ocean current energy converter technology is considered to be more mature than the wave energy converter technology. Now, we'll be looking some more details about that WEC, that is wave energy conversion system. Is there any question? Holly Cox, is there any question? Hello, Holly. Do you have a question?
No, sorry.
Oh, okay, okay. Okay, so as I told that WEC, that is Wave Energy Conversion Devices, convert energy that is contained on ocean waves into the electric energy. And typically there are two types of WEC system. One is called turbine type, and then other is called the buoy type. So, and then buoy type has received increased interest more recently, but the turbine type is the most common and the first to receive attention from the research community all over the world. So we'll be looking some picture and then power generation system from the turbine type and buoy type of the wave energy conversion system. So now first let's have a look at turbine type. Okay, so everybody say this is the example of some sort of turbine type of uh, wave energy conversion system. And typically that WEC are two types. One is called oscillating water column, OWC type, and then other one is called the overtopping type. So in this figure on that you are looking, those are the like OWC type, oscillating water column. So then for you I have explained something. Basically what is done in left side figure and right side figure, some sort of housing is made, and inside the housing there is already water. You know, this is anchoring system because these are located inside the sea or the ocean. So you need some anchoring system. So there is a housing or there is a chamber. So, and then there are some water. And then once there are waves, so it is coming from this direction or this direction, then water enters inside the chamber. And then for example, initially, this was the level of the water, and then there are just air pressure or the air inside. And once there is wave and then water level goes up, then there are piston or the shaft of the generator head that goes up. So therefore that goes up and down, kind of the linear motion type of, and then the power is produced. Same thing on the right side, you can see here is the TG, I mean the turbine generator, and then the shaft is connected. Again, there is housing system. This is some sort of closed chamber or the air chamber. And then already there are some water, but once there is wave, for example, wave coming from this direction, and then much more water enters, that water enters inside, and then that water hits the turbine or the blades of the generator. Consequently, it moves and it produces power. And as you can see, this is like coastline. Typically, these are located or situated pretty much nearby the coastline. So therefore, so everybody keep in mind, in this case, like there are already housing or some sort of container or chamber, and there are some sort of level of water. And then once wave is coming and wave is hitting, entering that housing, water level like water column oscillates, goes up and down, or the hits because water goes inside. And accordingly, the turbine moves, goes up and down, and then that produces the electric power. So now the next, the overtopping type, the other type in the next slide, this is the overtopping time example. In this case, again, those are some sort of encoding system. And this is some sort of similar to a hydroelectric dam. So therefore, in this case, there are some sort of water reservoir where there are some water. Again, this is the one sort of reservoir, like similar to that hydroelectric project, hydroelectric dam. There are water. And then once there are wave, You see, the wave is entering or wave is coming, and then the rotor or the piston is going down. So therefore, again, it is linear motion kind of going up or down. So same thing happening in this case. Once the wave goes on top of that reservoir, and then there is huge pressure by water, so there are piston or the rotor or the shaft that goes down. So therefore goes up and down, kind of the linear motion system, and then generator produces the power. So because in this case, the water is coming on the top side, accordingly it is called overtopping. And on the previous case, in this case, the water is hitting from inside, and then that is increasing the water level or water column. Accordingly, it is called like oscillating water column or oscillating water level. And then the next one is called overtopping WEC system. Now, moving forward, you see, this one, this is the third, it is called the buoy type. The first two one are the turbine type, and this is the buoy type. Again, there is some sort of anchoring system, and inside there will be some sort of piston, and depending on the wave crest or wave trough, the piston will go up and down. So for example, in this case, there is no wave example, and then right side you see, in this case, wave crest, when the wave is peak. So there is the piston, and then piston goes down. In this case, wave trough. So when it is at the minimum point of the wave, then that piston goes up. So in that way, like it is going up and then down, going up and down, and it is the floating type. That's why it is called the buoy type. So I have written here the buoy type WEC usually consists of a vertically submerged buoyant float that drives a power takeoff device such as a piston or linear generator. So in that way, this type and then the previous turbine type all are capturing the wind energy, the wave energy. Now, moving forward. Okay, so then so far I showed that how they are capturing energy, but ultimately how those captured energy are going to the electric network. So here you see that figure for tidal current device architecture. These are the current based. The previous was the wave energy based. This is the tidal current. So you see this structure or this turbine structure are typically placed inside sea. And once there is current or the tidal current, and then those blades or those parts moves. Consequently, that captures energy. And you see this flow diagram or flow diagram, that water current is hitting the blade, and then there is rotor, and then rotor shaft moves. And you see, similar to the wind energy system, there are drivetrain, there could be gearbox, and that makes a reasonable amount of speed. And that there is generator, and generator produce power. But then there are power transformer or power converter that produces required amount of power or the voltage to be connected with the electric network or electric grid system. So this is kind of the flow diagram in case of the tidal current. And then here is, you need not to be much worried about the inside control of that tidal current. Like it is capturing energy, half rho A Cp V cube, very similar to wind energy. And then Cp is function of lambda theta. There is some sort of pitch control device, then power control device, and then finally it is connected. So this is kind of representation of that system. So you need not to be much worried about this system. Just try to understand this flow diagram, how the tidal current or the current energy from the ocean can be converted into electric energy. So So moving forward, this is again another example of ocean wave device architecture. You see, basically these are like that buoy type, and they are collecting energy from the ocean wave, and then there is mechanical process, and there might be intermediate conversion stage, like high pressure turbine, intermediate pressure turbine, low pressure turbine, and then those goes to generator, and again there are power transformer, power converter, and finally that goes to electric power network. So and then again this is like that associated internal control diagram. So you need not to be worried much about this control diagram. And this is just showing how the ocean wave is varying, like the sinusoidal type of response. This is the peak or the crest. Here it is the trough, and again the peak. So this is called like the length, and this is called the height. And this is the like kind of still water level, that is the reference level. So moving forward, as you can remember that in case of wind energy system, onshore wind energy system, there were several types of wind generator and the electric machine. So in case of ocean energy or the wave energy system as well, there are several types of machine. For example, whatever it is, current wave or the ocean wave, whatever the technology is that we discussed, but then ultimately it is going to electric generator. Now, what this picture is showing, it is showing, the caption electric machines and power converters for ocean or marine energy system. Now, generator can be type 1 type, or it could be type 2 type, or it could be type 3 type, or it could be type 4 type that you have looked in case of wind energy system. For example, the first one, it is cage rotor, means squirrel cage rotor type of induction machine without converters. The next one is wound rotor type of induction machine, again without converter. But the third type, type 3, is that double-fed induction machine based and with partially rated converter. So maybe you could remember the diagram of double-fed induction machine that you have studied during onshore wind energy conversion system. And then this is the type 4, so permanent magnet type. And again, depending on the technology, whether there are gearbox or not, or how it is structured, they can be varying type with full rated converter. Even this could be like induction generator type, permanent magnet synchronous generator, or it could be even induction generator based. So in this case, in case of ocean energy system, that conventional induction generator is also called the type 4 type. So therefore, this structure, so you already know, so there is not that much new information. So far, everybody is fine?
Yeah.
Okay, thank you. Then moving forward, here you see, here figure 9, like network topologies for offshore energy collection system. Now, there can be various type of structure. As you can see, the top figure, it is called point-to-point topology. So point-to-point topology means, you see, one type of energy converter is connected to the onshore system, one at a time. Again, this is, for example, another, it is connected. I mean, of course, there are offshore portion and onshore portion, but it is showing the connection. This means point-to-point connection. all like independently or individually connected to the onshore system. But the next one is called the radial topology. You look the picture in the radial topology, like this is one energy converter, this is another, but all are connected to this common point. And then there might be again other units here, other type of energy converter, that is the meaning. And then on the bottom line, there are another set. You see, so again, all those are connected together and they are connected. Therefore, from here, all conversion systems are connected at this point, and then from there, that on common line goes to the onshore system. So that's why this is called kind of the radial topology. Now, this structure is called the ring topology. Again, you see it is pretty much similar to the radial topology, but you see it is called the ring because it is forming a ring. On the left side, basically this symbol, this rectangular part represents the circuit breaker. They are connected with the help of circuit breaker. So that's why this is called the ring topology. And then another topology, it is star topology. Like all energy converter are first connected in the form of a star. They comes to a common connection point, and that common connection point is connected here, and then again online goes to the onshore. So therefore, these are just the technology or the connection or the structure which are available so far. Now, again, moving forward, as I said you that we will be concentrating on that HVDC portion. That's when that offshore wind farm with HVDC line. So therefore, whatever the technology is, whatever the, turbine type or buoy type or other type, oscillating water type, all are collecting energy. And then here is that offshore AC substation, and then offshore HVDC converter station. And then from here, you see, until the onshore, that is the HVDC or the DC cable transmission system. So therefore, our concentration will be here. So the first question is, or a great question is, what is the benefits of having this offshore wind farm system over the onshore system? So I think in the next slide, if you see I have written several bullet points for you. You see that offshore wind turbines have several advantages, namely higher and more constant wind speeds, and consequently higher efficiency. Because there is abundant of wind speeds on ocean or inside the sea, that's why you could produce much higher power, and hence the efficiency will go high. That installation of offshore wind generator system is difficult as compared to onshore wind generator system due to the various reasons. First of all, turbine blades face stronger wind and wind shear turbulence. Because there are huge size of turbine blade. One blade is going at higher speed, other is on somewhat lower speeds. In that way, there are huge wind shear turbulence, and they face stronger wind. They can capture more energy, that is true, but they have to struggle a lot. And base or foundation, that faces strong sea or the ocean waves, current tides, even that earthquake. Typically, the earthquake is originated inside ocean or inside sea. So how about there is huge earthquake, and then the base and foundation of those offshore wind generator systems get loosed or broken. There is ship impact, and there is a ship impact because ship goes and then there are breaking ice. Those may hit as well. Salinity of water. Therefore, the constructing or the building base or foundation is costly. And maintenance cannot be done frequently due to weather condition. Although those offshore wind turbines or farms are not located inside the deep ocean, critically they are within like 50 kilometer or within 100 kilometer with respect to the shore point or onshore point, but still it is difficult to go frequently for maintenance due to the weather condition. So however, that unlike onshore wind generators, there are no restriction associated with obstruction. In onshore, there are buildings, mountains. Easily you cannot put wind turbine or wind generator onshore. There are land use dispute issue or the limited availability of loans. And the blade diameter can be larger because there is no building, so no mountain, nothing. So you can make huge size of diameter. And then if you remember that wind generator equation, half rho pi r square. So if you can make diameter high, this means radius high, so it could capture huge amount of energy. So therefore, although there are several drawbacks, but there are positive side advantages as well. So is everybody fine so far? Okay, so I'm assuming that so far it is fine. Then you see, now will we go some electrical side of that offshore wind generator system. We'll be looking much more dynamics and functionality of the offshore wind generator system. So here you see, I have mentioned offshore wind generator types. We already discussed. Basically, these three types, DFIG means doubly fed induction generator, PMSG means permanent magnet synchronous generator, and SCIG means squirrel cage induction generator. I mean, that was the type. This is type 1, this is type 3, and then this is type 4, basically. And then production and internal or external control methods are the same as the onshore wind generators. Energy storage is needed to minimize power and frequency fluctuation. And then typically, a static Bhatt compensator, which is called SVC, or static synchronous compensator, which is called STATCOM, is used both at the offshore grid point and onshore grid point. So that SVC and STATCOM are basically the reactive power compensator, which controls the voltage mainly. So therefore, these all are the kind of components and the equipment needed with the offshore wind generator systems. And these components govern the dynamics of the system. Now, let's see one realistic example. So you see this picture shows a realistic example from the electrical viewpoint. So everybody look on the leftmost side, there is offshore wind farm. This is that generator. In this case, this shows that DFIG type, doubly fed induction generator. RSC stand for rotor side converter, and GSC stand for grid side converter. And then there are some filters, and then this symbol represents the transformer, and then PCC means point of common coupling. And then again there is another transformer, and again filtering. Inductance, this also represents the filter. And then until now, this is AC. Now that is the HVDC converter substation. So sending it converter, this converter converts AC into DC. And then you see, because this is that HVDC line, so somewhat longer line, like 80 kilometer, or even it could be longer, 100 kilometer long. That's why you have to make a stiff DC to provide the smooth DC or ripple-free DC, there are the capacitor. And on the right side, receiving end converter, easily you can understand this is the DC to AC converter. And then finally, there is filtering on the AC system, and again connected with another transformer to match with the required on-source grid voltage or on-source grid system. Now here you see inside the HVDC system, in this zone, there is one thing I have written, DC chopper resistance. This one basically what happens, you see on the right side that red colored symbol fault, if there is any short circuit or other issue on the grid side, then impact goes to the rest of the network until generator, because all are like interlinked. So therefore, what happens, because here there are capacitor on the HVDC line. So once there is any fault, typically the capacitor voltage or the HVDC voltage goes high. Now, quickly you have to reduce down that voltage to make it a steady state value or the balanced value. That's why you have to quickly suppress those power. You have to quickly consume those oscillating power. That's why there is this resistance. And here, like for the protection purpose, there are two types. When this is working, this is not working, or when this is working, this is not working. For the safety purpose, there are two. Okay, so this is the basic configurations of that HVDC system. So therefore, that HVDC system is connected to the onshore grid with the offshore grid system. And that's why, that these days, as I said, that HVDC system has been very important. It has been very important subject matter. So the question is, what would be the type of the cable? What will be the design of those inverter converter system? Even that chopper resistance, or there could be other method. So lots of concentration is going on just on this portion of that HVDC system. Now, moving forward, here I will show you an example of a system case study. Once there is a fault on the grid system, as I told, because the impact will go on the left side, starting from this point until the generator shaft, the impact will go. So, and the main concern is the voltage. Because there will be fault, so immediately voltage here might go low. But you have to maintain a reasonable amount of voltage because customers are connected on the grid side. So that's why on term it is called LVRT. Everybody say LVRT means low voltage ride through. Low voltage ride through. Capacity enhancement of DFIG based offshore wind farm by using particle swarm optimization based DC chopper. Now, as you can see, as I already told in the previous slide, this DC chopper resistance is used to suppress oscillation, to minimize any voltage fluctuations issue or other issue when there is fault. So now, because you see it is controlled through a power electronics device, that's why how you will control that one. You could use simple proportional integral controller or other simple nonlinear controller, but always you need some sort of tuning of some of the parameter. That's why here I have used particle swarm optimization. The particle swarm optimization kind of optimization technique that can optimize your parameter. It can provide you a good set of parameters. That's why the case study is due to any fault on the onshore grid side, how we can maintain the low voltage write-through or the LVRT capability of the DFIG based system with the help of particle swarm optimization based DC chopper. DC chopper means this resistance. So therefore, in this case study, there are three scenarios or three situations. First situation, when there is no controller. Second scenario is with conventional DC chopper. Third scenario is with particle swarm optimization based DC chopper. So we'll make a comparative study uh, among these three cases. No controller. There is DC chopper resistant, but with conventional controller. Conventional means it is just PI, proportional integral type of controller. And PSO based controller means that I said particle swarm optimization. We are expecting that there will be some benefit using this PSO based DC chopper. Now, based on that, the highlight of that case study, that or the motivation or the background of this case study, that DC chopper is a popular solution for offshore wind farms LVRT. DC chopper is mostly used, and this has been very popular. And particle swarm optimization is a simple and fast direct search algorithm. I mean, there you might choose other type of optimization algorithm, like there is genetic algorithm, taboo search algorithm. There are lots of search algorithm or optimization technique, but PSO has been chosen because of its simplicity and its fast search performance. That's why that PSO can be utilized to improve the DC chopper performance. And what is the other motivation? Other motivation, existing offshore wind farm LVRT solutions are not intelligent enough. Because I mean, in this class, we are looking into modern grid system or smart grid system. That's why we want to apply some sort of intelligent controller or intelligent technique. That's why we are telling that existing solutions for the offshore wind farm are not intelligent enough. I mean, they are working fine, but we want to make it more smarter and more robust. So now, based on this study, I mean, in that system, depending on the application of the controller, whether it is conventional or it is PSO based, I've shown some sort of results. So everybody see, due to that fault, I'm showing, you see left side, OWF, means offshore wind farm, DFIG DC link voltage. As I told you, that even though the fault is happening on the right side, I mean, once again, even though we are considering that fault is happening on the rightmost side, but the impact is going until the left side, I mean, until that wind generator system. So that's why here is that offshore wind farm, that is the DFIG generator DC link voltage. So therefore, left side, the upper response shows terminal voltage profile, and then this was DC link voltage. So as you can see, I have shown that zoomed in portion here, that red card shows when there is no controller. So this means, you see, even though in the main figure, there is a huge amount of voltage spike or voltage surge. But with the help of conventional DC chopper or that particle swarm optimization based DC chopper, the systems can bring back to the original condition. Now, you see that that blue colored response is for the conventional DC chopper. So PSO based DC chopper is somewhat better as compared to that conventional DC chopper. And that is our expectation. Same thing happened for DC link voltage of the DFIG system. On the right side, you know, on the top response is DFIG speed response. So again, like speed, you know, that increased and then it was oscillating, but that proposed DC chopper both conventional and piezo-based, they can bring back the system to original condition. So, however, the performance of piezo-based DC chopper is somewhat better as compared to that conventional DC chopper. Now, this one shows that sending an station HVDC line voltage. This means HVDC line voltage at sending it. As I told you that even though the fault is on the one-shot side or the customer side, grid side, but still the impact goes rest of the network. So therefore, this response shows the HVDC line voltage. You see there is huge jump, huge surge or spike of the voltage on the line. So however, application of that DC chopper and then piezo-based DC chopper make the system stable. And you see that all these results, what was the scenario of the fault? Most severest one, like 3-phase to ground, which is called simply the 3LG. So of course, for other cases like 2LG fault and 1LG fault, you will get similar response, but the voltage surge magnitude will not be that high. So this is the most severest situation. So everybody is fine so far?
Yes, we are good.
Okay, so therefore moving forward, I think now based on today's discussion of that HVDC system and motion or wave energy system, I have set up some short questions or quiz for you. We already discussed, you just need to answer this one. And then again, as I told you, although still I did not upload the answers of the previous 2 classes that I said. Those are ready, but soon I will be uploading. Similarly, after the class today, I will be uploading the answers for these questions. But now I like you to participate with the answers. So everybody see the first question is, where and why is the high voltage DC, HVDC transmission system used in a smart grid? Explain your answer. So how would you answer this one? Where and why is that HVDC system used? So Othman, how would you answer?
I would answer like it used after the DC converter, and the reason we use it to reduce the losses of the transmission line.
Okay. Yes, the answer is right. And where, what is the best example? In which system that HVDC is used?
It's used for the wind generator of sphere.
Offshore wind generator system.
Yes.
So therefore, everybody see the appropriate answer would be like where. So in case of offshore wind energy system, because this means that HVDC system is used between the offshore wind energy system and then onshore power network. That is the location. And why is it used? To reduce the system losses. Because it requires less cable, there is no skin effect. I already mentioned those points, and there are less loss. There is only I square R loss. There is no I square X loss. So the next question, what is the motivation to use offshore wind farm, OWF? How would you answer this one? I can see Saraj Jafar. Jafar, could you answer this one? Jafar.
You can answer it, Dr. Ali, if you want.
Yeah, so could you answer?
Yes, because it can capture more energy and we can reduce the negative impact of having on sphere, because on sphere have negative views and it get affected by the buildings surrounding to it.
Okay, yeah, so like we already mentioned, there are one slide, dedicated slide for this one. There are lots of motivation. It can capture more energy because the wind speed is almost constant there. Okay, and then as I said again, I will be writing down the answers for these questions, and I will make these available for you. So as you can see here on question, can DC machines use be advantageous to observe wind farm generators? I mean, we discussed that we could use squirrel cage or DFIG or PMSG type, but I said if I use DC machine, then I am expecting that there are some advantage. So therefore the question is, do you think that DC machine use be beneficial or advantageous to offshore wind farm generator system? What
I
do you,
think it's not beneficial, Dr. Ali,
why?
because it does not capture a lot of energy as the AC machine.
But you see, because, why I am asking this question, because ultimately, even though you are capturing more energy, but you are converting into DC with the help of HVDC system. So my point is, if you use DC machine, then you can directly convert. You are directly getting the DC, which is needed on the HVDC line. So now DC machines can produce low amount of power, low amount of voltage. But if you connect it as DC to DC converter, like DC to DC boost converter, then you can easily increase the voltage. So then you don't need transformer, you don't need a power electronic interface. So in that sense, I would say DC machine usage would be advantageous or beneficial for the offshore wind farm. Do you understand?
Yes, makes sense.
Everybody, could you follow my question and answer? So like once again, because ultimately we are converting from AC into DC, and that we are applying on the HVDC system. That's why, I mean, the DC machine is helping you because directly you are getting DC, but because it produces low voltage, you just need the boost of DC voltage with the help of DC to DC boost converter. Then it is beneficial. Okay, question number 4. If an offshore wind farm generator is suddenly disconnected from the main power network, will there be any effect on the generator? Because you know that offshore wind generator, and then there is HVDC system, and again that DC is converted back into AC. There are lots of components inside. So what I am asking is, assuming that there is some issue with the main power network, and that main power network got disconnected. So does that have any impact on the generator itself? Do you think that the generator will be affected?
Yes, it will be because they are electrically connected.
Yeah. So what will be the impact? Will the generator speed go high, or what will happen? Because it is suddenly disconnected, so
Yeah.
generator speed will go high because now there is no load connected. So now the system inertia will be high, and then the speed will go high. So that is the impact on the generator. Now the next question,
Dr. Ali, would it be possible to be damage the generator because if we
yes,
can
yes, exactly. Or even though it might not be fully damaged, but you're right that certainly the impact will go on the shaft.
Okay.
Shaft system might be deformed, might be broken, yes, if not fully damaged. Yeah. Definitely there is impact. Okay, now the next question. Is it possible to transfer power between two unsynchronized power systems? this means that the meaning that two unsynchronized means, for example, there are two different frequency. One is 60 hertz and other is not 60 hertz. So therefore, everybody go back to that. Okay, see this system. For example, from the observing farm, that frequency, it is not 60 hertz. For example, it is 55 hertz or it is 65 hertz. But on the grid side, rightmost side, definitely it is 60 hertz for United States because that is the frequency requirement. So the question is, this means if left side is 55 hertz or 65 hertz, which is not 60 hertz, but right side is 60 hertz, this means that is not the synchronized system. Frequency is not the same. But it is possible to connect? So the answer is yes. So how? With the help of, the DC system. Because whatever the frequency here on the left side is, everybody see, whatever the frequency on the left side, because in between there is the DC system, so it is converting from AC into DC. Now that DC is independent of frequency, and with the help of this receiving end converter, you are converting into your required frequency. So the answer is yes. Two unsynchronized system can be connected. How? With the help of the HVDC system. So now everybody see the question was number 5. Is it possible to transfer power between two unsynchronized power grid system? The answer is yes. When I'm saying explaining how, with the help of HVDC system, because the DC system is independent of frequency. Okay, now the last question for today. Why is DC chopper resistance used with HVDC system? So why DC chopper resistance is used? What we learned? So what was our motivation to use that chopper resistance with the HVDC?
In case of any fault happen, the chopper resistor will reduce the high voltage storage in the capacitor to save the system.
Yes. Right. So therefore, that DC chopper will maintain the balance. It will consume the oscillations happened because of any fault on the grid system. That's why the DC chopper resistance is used. Okay. So everybody is fine. So is there any questions and comments? There are no more slides, but as I said, I'm going to write down the answers and I will make those available. Anybody have any question? And I think today, your due date to submit the homework set too. I noticed that some of you have already submitted, but I recommend you all to submit by the deadline. I think the deadline is tonight, 11:30, probably.
Sir, can we share in the Word format, right?
Yeah, of course.
Yeah, yes.
You just need to upload on that Dropbox homework too.
Yes, sir.
Yeah, you can make Word or the PDF file. You can upload that.
Sure, sir. Thank you.
But make sure that you all upload by the deadline. I think 11:30, because
Yeah, sure, sir.
after that you cannot upload. You know that when it is that in-person class, typically you have submitted during class, but because this is online system, and that's why I have given you the much flexibility. I have set up
Yeah,
time until the kind of midnight, but until 11:30.
yeah, I'll do it.
Yes. So, is there any question?
Yes, Dr. Ali.
Yes. Who is this?
For the project report, do we submit it by email, or are you gonna put like Dropbox for it?
I will create a Dropbox. I will create a Dropbox.
Okay, thank you.
You mean the written report, right? Yeah, I mean.
Yes.
Yeah. Class presentation, like you already emailed, and anybody can email, and I have already uploaded on request. But the class project written report that you have to submit to a Dropbox. Soon I will create a Dropbox. I will make that available for you.
And for the exam grade, did you already grade it?
I started. I could not complete, but soon I will be sharing. Maybe even today or tomorrow I will be sharing. I will email you all. No problem. I think I already discussed the answers, but I will make the answers available as I said. But soon, I mean today or tomorrow, I will let you know your grade.
Excuse me, sir.
Yes.
So, and regarding the project report, so like we are doing it for the first time. So, what I need to include actually the abstract part only regarding the topic.
Yeah. All regarding the topic.
Okay.
Yeah, kind of. You see that I think I have mentioned what you need: introduction, abstract, some methodology, conclusion,
Yes.
list of references. I would recommend you. You see that the paper that you presented in the class, you could follow that paper format in the Word file. You can
Yes.
you can choose to use double column format, or it might be single column format. So you might follow the procedure of that paper that you have read and gone through.
Means we need to take the main points from that and we need to put it in the each section, like in the abstract, introduction, background.
What you need to put?
Like we need to present it like a research paper or
Oh yeah. So therefore, especially the references that you are always showing at the end of the report. For example, we have 20 reference or 30 reference. Please
yeah.
use those references inside the text, especially the introduction section and your control or methodology section. In the abstract, you don't need to put any references, even though that is dependent on reference, but starting from introduction to until the conclusion, you can put any references.
Yes, sir. Thank you.
Okay. Yeah. So, Saresh Jafar, are you there? I can see you, but I'm not getting any response from you, Jafar. Okay, so does anybody have any question?
Yeah, I have a question about the homework. Question 2. Can you go over it? Maybe explain.
I forgot what was the question. What was the question number 2?
1 second.
Okay.
Said what should be the input and output variables to design controllers for an for an AVR and governor system for a synchronous generator located in the smart grid. Explain your answer.
Okay. So what did you write in the answer?
So for the governor, I think it utilized the terminal voltage for synchronous generator to a specific level, and the output voltage by controlling the area voltage of a synchronous generator. This what you're asking? I'm not sure.
Yeah.
Yes.
And then that's. And then you can explain the reason of your choice. Yeah. Like why you have chosen this input. For example, if it is AVR, as you said, you have chosen voltage. You just explain why have you chosen voltage. And then, for example,
Okay.
if it is governor, okay, speed is the input. So why have you chosen the speed? Or why it is output?
Okay.
Yes. Just what is input, what is output, and what is the reason to choose that? That's the question.
Okay. Thank you.
Okay. So anybody, any other questions? If no, then I am stop sharing the slides for today. Okay, everybody. So today I am ending it here. And so see you on Thursday. So hopefully next class I will be covering the demand response and somewhat the cyber security issues and the solutions. Okay, let's see. I can see some comments. Oh, hello. Oh, okay. Got it. Okay, so then, so bye everybody. So have a good day and please be safe. So see you on Thursday.